Okay, so this is, I guess, episode 2 of Journal Club. So we did one last week where we talked about paleoclimate stuff, basically thinking about if future warm climates are going to look a lot like past warm climates. And now we're going to be talking about, well, you want to take it off?
Well, we're going to talk about how aerosols, so pollutants that are in the form of droplets or dust, will influence the future climate by thinking about how they influence it now and how they influenced it in the last 100 years.
Yeah. So this is sort of more of a process-based paper than some of the ones we've talked about before, which were more like higher level thinking about how climate will change. And now we're talking about exactly like what is one of the mechanisms that will change climate and has changed climate. So for those who are just joining us, I'm Henri. I'm a grad student at MIT, and this is Raphael.
I'm Raphael, one of Henri's colleagues.
Yeah. So we're both third-year grad students, and pretty excited because Raphael is studying hurricanes and their role in climate and how they're affected by climate. So pretty excited to have an expert on this topic here with us. So you want to talk a little bit about this first paper, maybe read the title and then tell us a little bit about the overarching goal?
So this paper is aerosols implicated as a prime driver of 20th century North Atlantic climate variability. And the goal of the paper is essentially to influence, to understand what influence the activity of man could have had on the variability of the Atlantic, in addition to the impacts of the CO2 and the greenhouse gases, which cause the warming that we know. So the general knowledge, the general idea that were circulated in the field were that, well, the coupling between different systems in subsystems like the ocean and the atmosphere and land in the greater Earth system caused variability on various timescales, including multi-decadal variability. And that further changes were caused by putting greenhouse gases in the atmosphere. But what this paper is about is that other forms of pollution, like aerosol pollution, can actually have a large impact on the climate, and in this case, more specifically on the North Atlantic.
Yeah, so maybe before we get started with the paper, do you want to explain the there's two ways that we usually split up aerosol as affecting climate. There's what we call the direct effect and what we call the indirect effect. Do you want to give a very quick description of what those are?
Yeah, so the direct effect is essentially, imagine a very dusty day, and imagine that dust is your aerosols or whatever particles you are in suspension in the air. On a very dusty day, you won't be able to see very far because the aerosols interact with the visible light. And aerosols have the same effect on when put in the atmosphere through chimney stacks or car engines. You have these microparticles that get lofted and will either reflect or absorb a certain amount of the incoming sunlight, but also a certain amount of the heat radiated by the ground towards space. And the presence of these microparticles is going to affect a bit the radiative balance of the atmosphere, and that will then impact, well, where it heats and where it cools and the large-scale motions of the atmosphere. So the direct effect is really just the interaction of the aerosol itself with light.
And the net effect of that is usually to cool, right? When you add those aerosols, it usually cools by the direct effect?
Yes, so generally it is thought that over the global climate, aerosols cause a net cooling on the order of about 0.4 watts per meter squared. Currently, that's the direct effects of aerosols on the global climate. But the effect of aerosols is very sensitive to the distribution of size of the aerosol. So if you have larger aerosols, larger particles, they will tend to absorb more the sunlight instead of reflecting it. And this could cause more of a heating than we actually think. So the current idea is that the direct effect is a cooling effect, but it's not impossible that in some regions it's actually a warming effect.
Okay, so we have a quick question from Ben Walker. What % of the aerosols you considered are human-caused versus natural? And if it's a stupid question and natural aerosols have a different name, what is that name?
That's absolutely not a stupid question. That's a great question. It's also a good one, and I don't have a very good answer for it. In terms of volume or in terms of mass, definitely by far the largest amount of aerosols is natural aerosols, and it's dust and it's produced by deserts. It's going to be on the order of 5 petagrams per year for the Sahara. So that's a very, very large amount of dust.
And you can see that from satellite, right? If you just
yes,
look during certain parts of the year, you see this huge amount of dust coming off of the Sahara and over the Atlantic. You can literally see it just in visible light spectrum.
Yes, it's very clear. And although it's a much smaller mass, the sulfate aerosols, so the human emitted, which are human emitted, have probably a larger overall radiative effect. Although on the Atlantic specifically, it's debatable which one will have the largest effect.
Okay, so maybe do you want to give an even quicker description of the indirect effect?
Yes, okay. So generally the indirect effect is that the particles that form that are the aerosols are very good cloud condensation nuclei. That means that they are very good at helping water condense into the form of droplets and at helping clouds form. And so that can increase the cloud coverage, and clouds have very large climate effects, both again in absorbing heat emitted by the ground and in reflecting sunlight.
Yeah, and that's also one of probably the biggest single uncertainty in climate models right now has to do with exactly how aerosols interact with clouds and with climate.
Yes, it's a huge uncertainty, and even if you don't consider the interaction with clouds, even if you just consider the direct effect of aerosols, just on that there is already a very large uncertainty.
Okay, cool. Well, I think with that, maybe let's start getting into this paper. Where do you want to start with this? You want to start with this figure, or?
Yeah. So I guess this paper tries to look at the role of aerosols. In that case, it's sulfate aerosols, so no natural aerosols. It's really not the focus of this paper. So sulfate aerosols on the Atlantic variability. What this figure shows is essentially just the choice of the model for the paper. In black is reconstructions of sea surface temperatures. So for all three panels, it's essentially the same, which here we can take to be more or less the true sea surface temperature in the Atlantic. And the two top panels, so the top left panel shows an attempt to reproduce that sea surface temperature time series, that record, by using a certain model and it's not working very well, the CMIP3 models. And the second panel, B here, is an attempt to reproduce that same signal using the HADGEM model, which is a global climate model that is much more refined in terms of the way it treats aerosols in both the direct and the indirect effect. And it does a much better job at actually reproducing the signal. So that's why they're actually going to take this model. It's more or less a justification for.
Yeah. So Ben asks, is this correlation only, or does your model try to approach causation?
It's gonna discuss causation too. Here's just a little example of what it's going to look like. That's still for the CMIP3 model, so not the model.
They can't see your mouse.
So. Oh, okay. So sorry. On the top right panel is a little bit of a response to that, but that's still using the models that aren't very good. So what they show here in black is the reconstructed record. In red is the modeled record, and in blue is the modeled record with removing the aerosol indirect effect. And what it's attempting to show is that it's doing somewhat a better job when actually taking into account the indirect effect. But I guess that's going to be discussed a bit later on. Sorry, were you about to say something?
No.
Okay.
Go ahead.
Yeah, and also to reply a bit better to that question, causation is generally fairly, I wouldn't say easy to address, but the man-made aerosols are not influenced by the climate itself. They're not included into natural variability. They're an external, can be almost considered as an external forcing. And so it's not actually that complicated to establish causation from that point of view, I think.
Yeah, so usually the way that climate modelers approach these questions is you have a climate model, and then you can basically turn on or turn off different parts of the climate model. And then you sort of, while you do that, it's all sort of informed by the observation. But the way that you get at causality is by turning off certain things and seeing exactly how that changes the model run. And so if you turn something off and it totally messes up how much the climate looks like observations, that's a good indicator that that was pretty important for the climate physics.
Yeah. Also, I just see the question on the size of aerosols. I'm just going to answer it very quickly. So what's the size of aerosols? About 10 microns. 10 microns is a pretty big aerosol, and it would probably be more on the absorbing end of the aerosols that we find in the atmosphere. Scattering aerosols would be more of the order of 1 micron or even less.
And yeah, I think in this case, you're just turning off the human-caused aerosols. You're leaving in all of the natural ones, right? Or, oh no.
Not quite. It's not leaving out the natural aerosols, but models have been shown to do a very, very bad job at capturing the effect of, well, not a very, very, but a somewhat bad job at capturing the effect of Saharan dust. And it's not necessarily even included in that model.
Yeah, and that's the major aerosol in this region.
Yes.
We think.
Yeah. Yes, it is. And so that should probably be seen as a limitation of the scope of that study. Yeah. Studying aerosols over the North Atlantic without accounting for dust doesn't make a ton of sense, yeah. I think.
Okay. Do you want to explain what's going on in this figure?
So in this figure, it's mostly so the top panel of the figure, so panel A, is really just comparing the two simulations. One is the black line, and the other one is the field contour in red and blue alternatively. And the black line is the simulated temperature over the whole period, which is from the mid-19th century to the 2000s. And the field contour, and that black line fixes the aerosols. So has the greenhouse gases change and has natural variability evolve as it wishes, but has the aerosols fixed. And the second line includes the effect of the aerosols. And so it includes the effect of the variations in the aerosols. And as you can see, there is a pretty large difference on the order of almost 1 degree at the present day, on the sea surface temperatures at present day, if you have the aerosols or if you don't have them.
And that's a really big change because the ocean also takes a longer time to warm up than the atmosphere, for example.
Yeah, that's really a very big difference. The second panel shows the reconstructed shortwave radiations. I think that's probably averaged over the Atlantic basin. I don't quite remember how they did it.
That's okay.
Okay, yeah. And what they show is what they get from the model, which is again the field contour, by comparison to a reconstructed temperature that's estimated from what we know from the sulfates put in the atmosphere by the humans and by volcanoes. As you can see, there are some fairly strong spikes in the records, and those spikes correspond to volcanic eruptions, as can be seen on panel D of the figure, where each spike is associated with an eruption. And finally, on panel C is a comparison of different forms of aerosols to the aerosol optical depth. So essentially, to what extent it interacts with light. And in that case, we can see that it's really dominated by the sulfate aerosols.
Yeah, but this comes back to where you were saying that this model doesn't have the dust, and probably the dust would be...
The dust could be just as large.
Yeah.
Reading different papers, I saw comparisons I ended up comparing how much of an impact the sulfates had on precipitation in Africa and how much of an impact dust would have. And both impacts were extremely similar, the same order of magnitude.
Okay. All right. I think this is like really the key figure, right? These.
Yes, probably.
Okay. Do you want to maybe go through these quickly so we can get to the next paper?
Yeah. So these are really two figures. There is.
Let's zoom in on this one.
Yeah. Okay. So that's the difference between. If you recall, in the previous figures that we've shown, there were field contours alternating red periods, which were fairly high, and blue periods, which were fairly cold. And these figures show the difference between the cold and the warm periods. And on average. And on average, there is more aerosol burden during the coldest periods. And the pattern of the changes in aerosol, so in aerosol production, also matches more or less the pattern in the cloud fraction. And what's pretty interesting to see is this big empty spot in panel A, where there is essentially no aerosol at the center of the Atlantic. This figure is centered on the Atlantic. And that's because the aerosols come from Europe, and the ones that come from Europe go down with the wind in the tropics, and from North America, and the ones that come from North America go up north. And they never quite, there are places where they never quite make it because they're removed of the atmosphere on a fairly short time scale. The lifetime of a sulfate aerosol is probably about a week or something like that.
Yeah. So what this is showing us is that when it's cold in the North Atlantic, there are more aerosols?
Yes.
Okay.
Yes.
And I guess when it's warmer, there's less aerosols.
Yeah.
And this plot is showing that when there's more aerosols, you have more clouds.
Yes.
Okay. And that those are reflecting sunlight back to space.
Yeah.
And that's why we see this, which is...
And this is essentially the difference between in the short wave, so visible light, sunlight forcing in watts per meter squared between the warm years and the cold years, and over the tropical North Atlantic, it can reach up to 3 watts per meter squared, which is enormous.
Yeah.
It's a very big difference. That's on average for these years. And the last one is essentially just showing the difference again between the warm and cold years, both for the model, which is the panel D, and from the observations, which is the panel E. And the idea is to say that when you have aerosols, you capture patterns of variability that are similar between the nature and the models.
Yeah. So this is just like a check on their model to make sure that the process that they're saying is important is actually important.
Looks good, yeah.
Yeah. Okay, cool.
And then the last figure is pretty important, I think. Essentially, this one is to tell you, this one is just to remove the influence of the ocean variability.
Oh, yeah. So one thing we didn't say is that in the introduction of this paper, they talk about how there's like the main theory for why sea surface temperatures in the Atlantic change over the 20th century is because of changes in ocean circulation.
Yes.
And what they've done here is they basically stop the ocean from moving. And so any changes in the climate of the North Atlantic will have to do with this aerosol forcing.
Yes, exactly. And so both are very similar, and they even went further as to take the temperature at the top at the mid 19th century and impose the current aerosols, the aerosols of the year 2000, and that gives a shortwave radiation that is the one at the little star, which essentially just means that only aerosols are important, really. And if you go down a bit, that's just a comparison between the direct forcing and the indirect forcing that we discussed earlier. And you can see that the direct forcing is much, much smaller than the indirect forcing.
So what this is saying is it's not the actual reflection and absorption of the sulfates themselves, it's the fact that they affect clouds, and the clouds are reflecting sunlight.
Yes, and it can get very complicated because it can be because clouds form more easily because of the aerosols, but it can also be because, for example, over the tropical North Atlantic, if the sea is colder, it makes it easier for stratocumulus clouds, which have a large shortwave radiative effect, to form, even without the dust, just because the sea surface temperature is a bit colder, and that can feed back.
I see. Okay, I think we'll skip this one.
Yeah, that's fine. Just the same.
Okay, so do you want to? All right, let's see. We have a question from Ben. Well, I need some water. Do you want to take that question?
I think this one would probably be good for you.
Okay.
So, how do you make any conclusion about the ocean current theory? Is it less important or not important at all? It's a good question, and it's still a debated point. It is likely that the ocean currents are important, but the way that I would go about drawing conclusions as to whether they're important or not would be to remove all forms of aerosols and remove all other forms of variability. So human aerosols, I would remove that. I would remove the dust aerosols from the Sahara, from the simulations, and then I would rerun the simulations and see what is the magnitude of the variability. Mm. And my guess is that there would still be a fairly large, it would still be important. It's just that the aerosols are absolutely not negligible either.
Yeah. Okay, do you want to maybe quickly summarize what this paper was all about? Because I think a bunch of people joined us halfway through, and then we'll move on to the next one.
Yeah. So this paper was essentially about showing that the observed variability of the temperatures in the Atlantic, temperatures and climate of the North Atlantic during the last 150 years cannot really be explained without taking into account the effect of man-made aerosols like sulfates and their interaction with sunlight, and more importantly, that the most important interaction they have is through their effect on cloud cover and the interactions of the clouds themselves with sunlight.
Cool. So this was basically just looking at how aerosols affect sea surface temperatures. But one of the things they mention in this paper is that sea surface temperatures are really important for other climate things like hurricanes.
Yeah.
So hurricanes get their energy from heat in the upper ocean. And so if you increase sea surface temperatures, that's likely to increase the intensity of hurricanes.
Yeah.
And you know a lot more about this stuff because you've literally dealt with those models. And so now we're going to talk about this other paper, which directly tries to figure out how these human-emitted aerosols impact tropical storms in the North Atlantic, which we know as hurricanes. Okay, so do you want to maybe contextualize, or give a quick overview of how this paper is laid out before we go into it?
So we chose this paper to go to follow closely the paper on aerosol variability, on aerosol and climate, because they use the same models, which is the AdGem model, so a climate model that's shown to deal fairly well with representing the impacts of aerosols, both their direct and their indirect effects. And what they want to do here is essentially to show that the variability of hurricanes on a timescale of a few decades can partially be explained by the emission of aerosols. And why that's important is that if we can show that aerosols are important in controlling the frequency of hurricanes, then that allows us to make more precise predictions on what's going to happen with hurricanes. Because if we stop emitting aerosols, that might actually increase the frequency of hurricanes, even if we don't change the greenhouse gases at all. And that's what that paper is focusing on.
So maybe a little bit of context is a really basic thing in climate science is that as you increase greenhouse gas concentrations in the atmosphere, you're going to warm the planet, you're going to warm sea surface temperatures, and that's going to energize storms, and in general cause tropical storms to be either more frequent or stronger.
Yeah.
However, it could be that part of the reason we haven't seen that in the observed record since we've been increasing concentrations is because we've been sort of masking that effect by a compensating effect due to aerosols.
Yeah.
Or the other way around. If aerosols have decreased over a period of time, maybe that you see a spike in hurricanes during that period or something.
Yeah.
Oh, how's it going, Uncle Bill and Paranor? Welcome. Okay. Let's dig into. Okay, so this first figure basically just so these first two columns are looking at the historical record. So this is 1850 to 2000, and then the last column looks at the future. And so the first column is like observations, and the next two are models. And so these are like 4 different indices, which we're going to go through, and they relate to tropical storms, some of their causes, and sort of related factors.
Yeah.
So you want to explain what the major features of this are, and also they can't see your thing. I was wrong.
Right. So the first one is simply the storm frequency from the HERDAT data set. So it's observed and reported storms that extends for the past about 150 years. So that's panel A. Panel B is the simulated storm frequency using the HADGEM model. It's not doing absolutely the best job, but it captures the phases where there are more hurricanes than average, and the phases where there are less, which is really what.
So this positive frequency here means it's more hurricanes than the century average, and blue means less hurricanes than average.
Yes,
okay.
yes. And then you also have the same on the same comparison between data and precipitation. Data and model for the main MDR is main development region, so where the hurricanes happen, for different variables that are thought to be or shown to be important for the hurricane formation and development. So D and E are for the precipitation in the main development region where hurricanes happen. I think this panel is really just to show that it captures climate, the model captures climate in a similar way as what really happened. The panels G and H show the wind shear in the main development region, so the difference in wind speed between the near sea surface and the upper levels, and that has that is very important because a higher wind shear is associated with is bad for hurricane formation essentially. And so as you can see, if you compare A and G, for example, when there are a lot of hurricanes, there is generally low wind shear and vice versa. And
the way to think about this is that hurricanes have sort of like a very uniform wind with depth, right? Like from the top of the hurricane to the bottom, it's pretty uniform. And so wind shear is sort of like tearing the hurricane apart. Is that the right way to think about it?
It's not uniform, but it's a very vertical structure.
Okay.
And what wind shear will do is it will, you can consider it as pouring water on a fire a bit, is it will cause mixing in the inner core of the hurricane, which is extremely moist and extremely warm, and it will bring dry, colder air in the inner core of the hurricane, where it will decrease its efficiency, essentially, is the general way to see it.
So side real blue says warmer oceans equals more energy, so stronger storms, but more aerosols could have to do with, is related to wind shear, and so that might offset that and cause less storms. And I think we're going to get to that later in the paper, right? They have.
Yes, definitely. And more aerosols is more wind shear, but there's also generally in the Atlantic a colder ocean. And so it's both the different studies have talked about the fact that aerosols would increase wind shear, and that was bad for hurricanes. And other studies have said, well, it decreases the difference in temperature between the sea and the air right above. So it decreases sea surface temperatures, and that's bad too. So these two mechanisms can really be at play and are both driven in the same direction by the aerosols.
Yeah.
Should we?
Yeah, it's just temperature.
Yeah. Right. So here is where it gets really interesting, is the fact that in the pink time series is a simulation in which you have no aerosols, but only the greenhouse gases. And the green time series is only the aerosols and no greenhouse gases. And the black time series with the filled-in filled-in profile, so in the red and blue, is all the different forcings. And it's really clear that, at least to me, it's really clear that there is much more of a similar pattern in variability if you take into account only the aerosols, as to if you take into account the greenhouse gases. So the idea here is to say that in the Atlantic, at least, it's possible that currently, and for the last 150 years, aerosols have had a larger effect on the frequency, the occurrence of storms, than greenhouse gases have had.
So I have a question about this figure.
Yeah.
It seems that it's saying that when you have just greenhouse gas emissions, that it's still causing storms to become less frequent, right? This pink curve has a general downward trend.
Yes.
Do you know why that is? Because that sort of goes against what we were saying earlier.
So I don't know that it's been established that storms would be more frequent perhaps I wasn't.
I think it's that strong storms would be. So maybe this is not looking at strong
because this
storms.
is storm frequency. And if you look at, there are other papers, one by Villarini and Vecchi. Anyway, if people are interested, I can. That shows, that compares the power dissipation index, which is essentially the integrated energy dissipated by the storm over its lifetime.
Okay.
And that will increase both if you increase the frequency of the storms, and if you increase its lifetime, and if you increase its intensity. So it's kind of a compounded effect of all of these. And the power dissipation index can be shown to be increased both by increasing greenhouse gases and by decreasing aerosols.
Okay.
So in the future, if we continue to pollute but have stronger clean air regulations, so if we continue to put CO2 but have stronger clean air regulations, both increasing the CO2 and decreasing the sulfates would increase the power dissipation.
Okay. And the power dissipation is just sort of like maybe a better way of thinking about the strength of hurricanes, because it's not just looking at how strong a single hurricane is, but like if you average over some really long time, like how much energy went into those hurricanes.
Yes, especially since the power dissipation depends on the velocity cubed in the hurricane. And so that stronger hurricanes are really weighted more than the smaller ones.
Okay.
And this one here is using the CMET models, which we've discussed earlier, don't really capture quite as well the aerosols effect and Atlantic variability, as does the AdGen models that's on panel A. But we can still see that that the indirect effect of the aerosols, just like in the previous paper, is again very large in this case. In the CMET model, they're not talking about storm frequency, but the difference in sea surface temperature between the main development region and the rest of the tropics. So that's the y-axis. The reason why they're doing that is probably because it's not resolving tropical cyclones very well and not reproducing the distribution very well. and so they're using this sea surface temperature difference as a proxy.
Okay, so they're just saying this probably relates to storm frequency, but they can't really do any better than that with that model.
Pretty much, yeah.
Okay. Do you want to just skip to the next one, maybe, or
whichever?
Yeah, let's go to the next one. Okay, let's zoom way in. Okay, you want to talk what's going on here?
Mm-hmm. So this essentially compares the two different climate scenarios. So the RCP 4.5 and the RCP 2.6. Henri knows more about that than
me. So these are the same types of scenarios we talked about last week. So the numbers at the end of RCP stand for the watts per meter squared, which is like how much energy or power really is coming into the Earth by the end of the 21st century. And so this scenario relates to if you stop increasing greenhouse gases and sort of rapidly transfer your energy production to renewables, like in the next couple decades. And then the 4.5 scenario is sort of like a middle ground scenario. If we continue to mostly rely on fossil fuels, but sort of slowly get transition to renewables. And so these give us sort of two different versions of what the world might look like in the next 40 or so years, I think, for these figures.
And one thing that's very, very interesting here is that in the RCP 4.5, which is the warmest of the two cases, where the entire world globally is warming most, there is a little bit of heating in the main development region, which is the tiny square centered over the tropics. That region. And so there is a bit of warming, as you'd expect in a climate warming, global warming scenario. But in RCP 2.6, there is actually even more warming over the main development region. And while that can seem a bit counterintuitive, it is because in the RCP 2.6 scenario, you stop increasing the greenhouse gases, but you also remove all of the aerosols from the atmosphere on very short time scale. And so on short term, the effect of removing the aerosols from the atmosphere through rain and dry deposition is actually larger than the effect of continuing to put CO2 in the atmosphere while keeping the same aerosols.
Yeah, so Ben was quick on that. He noticed that there was more warming in the North Pacific too, and it's the same reason. So in RCP 2.6, China and India and Japan are rapidly decreasing all emissions, not just greenhouse gas emissions, but also aerosols, which is going to warm the North Pacific because you have this wind that comes off of China and Japan and goes this direction over the North Pacific. So I think that's why, again, you're seeing more warming here than in this scenario. This is sort of a short-term projection. So this is just looking at, I think, the year 2040 or something.
Yeah.
So if you went all the way to 2100, at that point, probably RCP 4.5 is already quite a bit warmer, pretty much everywhere.
Yes. Yeah. And the rest, these panels are essentially just to show that, well, it has fairly large impacts on the precipitation as well. Just a side note that I think is fairly important is the fact that over the North Africa and in the Sahel region, there is an increase in precipitation in both scenarios. And in the RCP 2.6 scenario, it's really due to that decrease in aerosols. And I won't talk about it too much, but aerosols really have been shown to be responsible for massive droughts in this region and massive humanitarian crisis. So it's a bit, yeah. It's and the wind shear. Yeah, so we've discussed about the sea surface temperatures, and also there is also the impact of the wind shear, which there was a question about earlier, and we can see that the wind shear in the RCP 2.6 decreases for even more than the wind shear than it does in the RCP 4.5. So 4.5 would be panel G, and which again says that in the RCP 2.6 you would have even more enhancement of the hurricanes.
Yeah. So it's sort of a counterintuitive result.
Yes, very, very much so. Perhaps it would be good to just go back to the first figure. You know, the word of projections?
Yeah.
And I think it makes much more sense to look at them now.
Yeah, I agree.
Yeah, so the panel C.
So this is like, let's look at that. So these panels are starting at 2000 and going all the way to 2100.
Yeah. And you can see that there is this almost delta function in the frequency, storm frequency for RCP 2.6.
A rapid drop after about 2020 or 2030 or so.
Yeah. And so but it increases initially a crazy amount, the storm frequency, and then it eventually decreases. But you have this initial very rapid increase due to the removal of aerosols, essentially.
Yeah, it's pretty cool. So basically all of this big jump here from like, what is this, 1980 or something? Yeah, like 1980 to probably 2020 or 2030 or something.
Yeah.
And then after that, you might have lower storm frequency.
Yeah.
Cool. Is there anything else you wanted to add, or?
Well, just drive the nail that this model has about this HAPGEN model has about 80% of its aerosol effect that comes from the indirect effect, and it does reproduce the observed variability well, but there is just a small problem with that, is the fact that it is possible as well that the aerosols would be, how would I say that? Is that it's been criticized that we don't actually know very well how much the aerosol indirect effect is, and that their estimates seemed to be on the high end.
Oh, okay.
And it reproduced the multi-decadal variability fairly well, but it could also be that the aerosols are influencing different climate feedbacks around the world, which force that variability. It is not necessarily the indirect effect. So it is certainly important, but perhaps it's a bit overstated here.
So it might be an indirect effect.
Yes, that's
Cool. Does anyone have any questions for Raphael before we wrap things up? That was cool. Yeah. So first paper about aerosols and climate, and then trying to connect that back to the tropical storms. And Raphael's working on this for the next while.
What does your shirt say? That says Génie Aéro. It's from in French, and it's from my undergrad. It's a very, very old Sunday T-shirt. That's from aerospace engineering when I was an undergrad.
Yeah, Raphael has a very solid grasp of fluid dynamics, partially because he got the really rigorous treatment in all of the mechanical engineering and aerospace engineering classes, right?
You're flattering me, Henri. I'm not sure if I'm doing that good.
That's my take on it anyways. Cool. So I think I haven't found someone for next week yet, but I think we'll do another one of these paper ones. We might do, I don't know, what do you guys think? Do you guys like the 2-paper format, or do you think it'd be better if we did like more in depth on 1 paper? Or would you like to do like more general lectures? What do you guys think about this format? You know, either let me know now or send me an email or DM on Twitter or something, or post in the Discord. Oh, hey, how's it going? You want me, Johnny? Okay, you only caught the second paper. Second one was the most important one of these two. Cool, yeah. Thanks for 1 paper at a time? Okay. All right, so I think maybe next time we'll do 1 paper at a time, and we'll do a deeper dive But this was nice because at least the 2 papers were related. Last week was just 2 completely unrelated papers. So I don't know how good that was, especially because one was about economics, and I have no idea what I'm talking about with economics. Cool. All right, thank you guys so much for the feedback, and thanks for watching.
Thank you.
Yeah, so I'll post on the Twitter and maybe in Discord who the guest next week will be. Might try and get someone from Harvard because they study kind of different stuff over there than we do. That would be cool because I also don't know those people very well, so it'd be nice to make that connection. All right, thanks everyone. I think we're gonna head out. I'm still a little sick, so my voice is wrecked. But thank you, Raphael, for doing most of the talking.
Thank you.
All right. See you guys next week. And we'll be playing probably Civilization 6 on Tuesday, getting ready for the new expansion coming out soon. Yeah, I should have some cool. All right. Thanks, guys. See you.